When I teach this class in a regular classroom, after we work challenging problems, I always like to say that we restored the universal harmony. That's, of course, if we get it right. And boy, after that last video, I feel like I have really restored the universal harmony. So this problem won't be so bad. This is number 26 on page 282, and it reads y double prime plus y prime minus 2y equals to 3e to the negative 2x. Now, it looks like it's a case we did earlier, where we did this exponential shift theorem. Y particular was equal to, I'm trying to do this from memory, I think it was be to the ax over p of a. And in this situation. And the problem is that it won't work on this case because p of a is going to be 0. So I'll show you all that. And so this ends up being, if you're keeping score in our book we've been using, it's case 6 in this topic. Well, okay, let's look at the operator. It is d squared plus d minus 2 operating on y is 3e to the negative 2x. So y particular is 3, 1 over, and I like to factor that 3 out, 1 over d squared plus d minus 2 operating on e to the negative 2x. All right, I guess it's optional whether you factor that 3 out or not. We can do that at any time. Let's go ahead and factor this. So this is y particular will be 3 over d plus 2 times d minus 1 operating on e to the negative 2x. So this factors as d plus 2 times d minus 1. And here's the issue. You see, minus 2 will cause division by 0. And so if I just went ahead and applied that one theorem that we've seen before, then this would be the polynomial operator on negative 2. And when you plug it in, you're going to get 0. You get division by 0. So that method does not work. Okay, well, then we need some kind of alternative here. Now, we could think about it this way and say, well, this is 3 over d plus 2 times 1 over d minus 1 operating on e to the negative 2x. And at least we could apply that theorem there, and then we could do a expansion on 3 over d plus 2. So we could apply that slick little theorem, exponential inverse operator shift theorem, and it would work on this term, and then do an infinite series expansion on that term. Okay, so there's a technique. But the author has worked out a nice theorem, and it looks a little complicated. So in this book, it is on the bottom of 278, page 278. So I'm going to erase this part here. And I think I'm inclined to write out the theorem. The theorem says that if P of D is d minus a raised to the r power times f of d, then y particular is going to be 1 over p of d operating on b e to the ax, which is what we have right here, where b is equal to 3. And then the theorem says that this is equal to b x to the r power e to the ax over r factorial capital F of a. So that's kind of nice little theorem there. And again, the f of a is, in this problem, would be f of d would be d minus 1. Alright, so let me erase up above and we'll apply all this and wrap this problem up. Well, let's see what we got. So y particular is going to be what? Well, b is 3, and r, if we take this, you see f of d is going to be d minus 1, and so a is going to be negative 2. A is negative 2, and we know that from here. Here's e to the ax, and then so we know what f of d is. It's this factor, which does not disappear when you plug in negative 2, when you plug in a. And then r, what in the world is r? R is going to be 1 in this problem, because p of d is equal to a d plus 2 to the first power times d minus 1. So do we have all the ingredients? Oh, I think so. Anyway, so we have b, 3, x to the r power, x to the first power, e to the ax, e to the negative 2x, over r factorial, that's 1 factorial, which is just equal to 1. And then f at a would be, now f of d was, here it is, d minus 1. So when I plug in a, which was negative 2, f of negative 2 would be negative 2 minus 1. So this is negative 2 minus 1. Well, 1 factorial is 1, negative 3 cancels positive 3. I get minus x e to the negative 2x. So here's our answer. Y particular is minus x e to the negative 2x. Well, let's double check that. Trust but verify. And yep, that's the answer they got. So handy little theorem for some exceptional cases. Now I don't know if that comes up in real life. How often would you, first of all, get a differential equation with nice constant coefficients where the characteristic equation factors, and you could use an operator method like this, but your right side happens to have in the exponent of e a root from your polynomial operator or characteristic equation. How often is that going to happen? Well, that's okay. We know how to deal with that, don't we? And so it's a nice little theorem to have around. Okay, well, the very last case, case 7 in this book, deals with when q of x, the right-hand side of your differential equation, is a sum of different functions. And so all it does is just justify that you can take the inverse polynomial operators and distribute them across those sums. So, for example, if you, let me just make up a problem real quick. Well, that was pretty quick, wasn't it? Suppose we had, I just made this up, y double prime minus 3y prime plus 8y equals to x to the fourth minus 3x squared plus cosine 2x minus 4e to the negative x. It just simply says that we can apply our polynomial operator, inverse operator, 1 over p of d. We can apply it to the first term and the second term, 3x squared, sorry. And the third term, cosine of 2x, and the fourth term. Anyway, the case 7 just justifies it. Says that we can split that up into really basically 4 separate problems if we wanted to, using operators. So anyway, that's our complete introduction to linear operators. And next we're going to look at a different type of operator known as the Laplace transform.